When we sketch a sine curve, we usually start at the origin, then go up and down and up and so on. But we know how to deal with the situation where the graph is shifted over. I'm trying to make this clearly the same graph as the white one, but shifted over a certain number of units. Now, if my white graph is exactly sine y equals the sine of x, then my yellow curve is also y equals the sine of x, but it's been shifted over. So let's write the equation for y equals the sine of x, where we can represent the shift algebraically by including a minus c here. And let's see if we can figure out what c is. Now, I said a minute ago that y equals the sine of x was my white curve here. That means its amplitude is 1. It hasn't been stretched or compressed in any way. So it goes up to 1 and down to -1. And therefore, so does the yellow graph. It goes through 0, pi, and 2 pi at the x-axis, or it goes through the x-axis at 0, pi, and 2 pi. And therefore, its maximum, and where the yellow graph appears to be starting, is halfway between 0 and pi. So that's pi over 2 right there, which means my yellow graph is starting pi over 2 units to the right. So I can write this as minus pi over 2. Now, that should just be review from what we have done in the past when we were learning how to graph sine and cosine functions and transformations of sine and cosine functions. In this case, we're looking at this as a review because I want to talk about this horizontal shift. In an application, and electrical engineering is certainly one of those places, we often see sine or cosine graphs and we see them shifted. And by shifted, I mean we're just not starting at 0, 0. Remember that this yellow graph goes on in this direction as well. Graphically, we say it's been shifted to the right. Algebraically, we say x minus pi over 2, but it's still just a sine graph. We could think of it as a cosine graph. In this particular case, because it's been shifted pi over 2 to the right, we could think of it as negative the cosine of x. But that's a transformation too. So let's stick with y equals the sine of x for now and talk just about this horizontal shift. So oftentimes, rather than thinking about this as a negative cosine, I want to think of it as a sine, but then I have to think of it as being shifted. The vocabulary involved here is that in the applications, this is called a phase shift. Let me write that down. Here's our generic formula for a sine or cosine function that's been amplified, moved to the right or left, had a number of periods included beyond 1 between 0 and 2 pi, been shifted either up or down. In this context, C is what we call the phase shift. Remember that this formula can also be written as A times either the sine or cosine of just bx minus, in this case, it would be bc plus d. And then in order to find the phase shift, we have to factor out that b. So, for example, you might see d of t equals 3 times the sine of 5x minus 10 plus 4, which to find the phase shift, I need to factor out the 5. The phase shift is 2, not 10. Another way to look at this is as though we're going around the unit circle. So looking at my white graph here, let's just pick one cycle. I'll grab a thicker pen and I'll go over one cycle. All right, that's the graph of y equals the sine of x between 0 and 2 pi. On the unit circle, that looks like this. With a radius of 1, start at the angle 0 and go around in the counterclockwise direction until you get back to where you started. This is both 0 and 2 pi. Looking at the yellow graph, I've started at t equals 0, I start below the x-axis. If I wanted to start here, I'd be looking behind me to see where my graph actually goes before I get to this so-called starting point. So in this case, my unit circle would look something like this. Start at negative pi over 2. Grab the wrong color there. Start at negative pi over 2 and go around the circle until you get back to where you started. You can actually think of this a couple of different ways. You can either say, I'm graphing the same thing, but at a different time. I'm starting late. Or you can think of it as graphing something different at the time, wrong color, sorry, graphing something different at the same time as you were graphing the original function. Either way, you're starting in a different place, but going in the same direction and covering the same ground. I would like to point out that this diagram isn't quite accurate because I said when I drew my white circle that my radius was 1. Well, if that's true, then the radius of the yellow circle is not 1. But I was only using this as an illustration, so assume that the radius of both of those circles is 1. The reason that's important is fairly minor. Either it's going to take you longer to go around this outside circle because it's actually a bigger circle if you go at the same speed, or if you want to get around this circle in the same amount of time as you got around this circle, then you're going to have to go faster. So either your speed has to change or the time will change that it takes you to do it. Remember that with the white circle, we were starting at 0 and going around, oh, I missed that time, until we got to where we started. And with the yellow circle, we started down here and went around and got back to where we started. The angle in between them is called the phase angle. We can see that angle in our original graphs as well, the difference between the peak of this graph and the peak of this graph, or the difference between the beginning of a sine cycle in this graph versus the beginning of a sine cycle in this graph. So the difference in the two here is represented by the shift, the horizontal shift, that phase angle. There's one more new piece of terminology here, and that's phase difference. I find this term very confusing and a bit misleading, so I'm actually not going to talk about it on this slide. I'll talk about it on the next slide, where I can show you what it means in context. So at this point, we're going to go to an example. Here we have two functions, and right away I can tell they're going to be similar because they're both sines, and they both have an amplitude of 10. They also both have this 3 in front of the t, which even when I factor that out, is going to remain in the position of b or omega or k, depending on which particular part of the textbook you're remembering that from. That's going to be 3 in both cases, even after it's factored out. So the graphs of both of these functions are going to be sine graphs with amplitude 10 and with 3 cycles between 0 and 2 pi. The difference is in the phase shift. Each one has been shifted from a sine graph by a certain amount. Now, it's not pi over 6. It's whatever I get when I factor out the 3 here. I get t minus pi over 6 divided by 3, which is pi over 18. Let's do that with the other one. If I factor the 3 out, I get t minus pi over 2 divided by 3, which is pi over 6. So the graph of this function has an amplitude of 10. It has 3 cycles of the graph between 0 and 2 pi, which means we can figure out what its period is. It's 2 pi divided by 3, 2 pi over 3. And it has a phase shift of pi over 18. This function also has an amplitude of 10. It also has a period of 2 pi over 3, and it has a phase shift of pi over 6. The reason I put two functions down here is I want to talk about how they compare to each other. Specifically, I want to talk about what's called the phase difference. This is where I think this terminology is a bit confusing. It seems as though if this is the phase shift of one function and this is the phase shift of another function, the difference of these two values would be the phase difference. But it's not. It's not defined that way anyway. It's defined as the difference between these two values. Now, Notice that the 3's here have to be the same for us to be able to talk about a phase difference. But then we're going to talk about it as being that pi over 2 minus pi over 6, the values we had in those positions before we factored out the 3. Now I'm multiplying by 3 here just to get a common denominator. This gives me 3 pi over 6 minus 1 pi over 6. So I can combine those. That's 2 pi over 6 or pi over 3. This is my phase difference. Because of the nature of sine and cosine graphs, if this number is a multiple of 2 pi, then the two graphs are going to overlap each other. You wouldn't be able to tell by looking at them which one was the equation from this function, and the graph from this function, and which was the graph from this function. So when that happens, we say the graphs are in phase. It's kind of like thinking of them as being in sync. If this number is not a multiple of 2 pi, like this one here, then we say the graphs are out of phase. That's really pretty much all I want you to get from this topic. There's a really nice exercise in your textbook, number 61, about two fans, that does a nice job of summarizing the skills that you need from this topic. It asks you to find a couple of equations for the behavior of the two fans, but from two different perspectives. For the first fan, the point at which you want to start thinking about the rotation of the fan and therefore building your equation, that point starts where the angle of rotation is 0. For the other fan, you start where the angle of rotation is 3 pi over 4. So the first one is probably going to be a sine function. The second one can be written as a sine function, but it'll have to have a phase shift. I like this topic, but it's really kind of beyond what we really need for our work with trigonometry. So this has been a nice introduction to it. You'll see it again if you take physics or engineering classes. But for now, I think we've done enough. This is the end of the topic, the end of the section, and the end of the third unit of the course, and we're completely done now with both chapters 5 and 6. I know we've been jumping around a lot, but we're done with that now. Once you take this quiz and the exam, we're going to be starting with chapter 7.